Hi chemists. In this video we're going to talk about reactions that happen in solution and how they're different to other states, just briefly, and then we're going to do some harder quantitative chemistry calculations. A couple of problems there. Okay, so let's talk about reactions that happen in solution. I've got some diagrams here on the right which I put in as an animation, but they haven't worked out because it's a PDF, but I can talk through them anyway. So reactions occur readily in solution as the reactants have easy access to each other. Okay, it's similar to a gaseous reaction where these particles can approach each other in 3 dimensions and they're not kind of hidden. Let's contrast that to a liquid. When two reactants are liquids, they can only react where they're meeting each other at the interface between the two liquids, okay? And when they're a solid, they need to be shoved together. So they're again only reacting at an interface where you've actually physically made these two crystalline solids meet together, okay? So solid reactions tend to happen very slowly. Liquid also a bit slower than gaseous reactions because again interface, but they can mix a bit better being liquids. They want to fill their volume. But gaseous and reactions in solution happen quite quickly because they're kind of moving about and they can access each other in all 3 dimensions. So I've tried to show that here with a gas reaction up the top. A solution reaction is a second. So gas, aqueous, these are nice labels that I should have put in. Liquid, and then a solid. What I'm trying to show you is, in animation, we've just got snapshots of it, is how these react. So there they all are, the pink and the yellow. Sorry, the pink and the yellow. The purple and the yellow. Don't even know my colours. And I've put a barrier in between. So we're going to remove those barriers. And you can see that as soon as you remove the barrier, the gaseous reaction at the top has pretty much gone to completion. They all react really fast because they're bouncing around really fast and they've got easy access to each other. You can see that the aqueous has started to react in the middle here, okay? But outer still hasn't happened, and the liquids have started to flow together and you're getting reaction at the interface, and the solids you're getting a bit of reaction at the interface, but much less than the gas and the aqueous. Move on to our next snapshot. The gas is gone, the gas is all done. You're getting more molecules in the aqueous react together. You're getting a couple in the liquid, and the solid still pretty much just not much, but only at the interface there. Okay, next snapshot, gas is all done, but here you've got the aqueous state all done as well. There's a bit of excess purple there, but pretty much it's gone to completion. Here, a few more molecules in the liquid have gone, but still not very fast. Here, maybe a couple of the solids have mixed together. So you can see that the reaction rate happens differently for different states. But anyway, on to some harder problems. That doesn't quite connect, but that's okay. I needed to talk about that anyway. You need to understand that. A couple of harder problems. What volume of this concentration of hydrochloric acid is needed to react completely with this mass of zinc? Okay, so we've got to have a reaction between zinc and hydrochloric acid. We need to completely react away all the zinc. So we need to work out how much hydrochloric acid we need. And it's saying you need to deliver that by this concentration of the acids. So it's saying how much of that volume do you need? So a little bit tricky again, but let's start with a balanced chemical equation where we often start when we're talking about reactions. What do we got? Hydrochloric acid, aqueous, plus zinc, solid, going to, okay, we've got an acid and a metal, so we're producing hydrogen gas, and a salt, okay. Zinc must be the cation. And what's left over from the acid? The chloride, so it must be zinc chloride. Zinc 2+, chloride single minus, so ZnCl2. And because hydrochloric acid is there and it's aqueous, and zinc chloride you'll come to know is soluble, that will be a soluble salt. So it'll be in solution there, the zinc chloride. Okay, let's make sure we're balanced, and we're not, because we had to... zinc chloride is ZnCl2, so we need 2 hydrochloric acids. And that gives our 2 hydrogens to make H2 there. So we're all balanced now. Okay, what do we got from the question? Let's have a look. Let's change colours. We've got our hydrochloric acid concentration is 1.47 moles per litre. That's not the best colour, is it? And we've got 2 grams of zinc. Okay, what we can do is go down to moles of zinc. Okay, work out how many moles of HCl needed. And then from the moles needed, divided by the moles per litre to give us the volume. Okay? Alright, change to a blue. Okay, so moles of zinc is going to equal our 2.0 grams divided by the molar mass of zinc. Look on our periodic table, it's 65.38 grams per mole. 65.38 grams per mole. We'll put it in our calculator and it'll tell us how many moles of zinc we have, because mass is horrible and we don't like it as chemists because everything weighs different amounts. 65.38, and I get 0.0305. 0.0305 90 moles. Why not add a lot of significant figures in there? Okay, so I've got that many moles of zinc. How many moles of HCl do I need? It's going to equal our moles of zinc, 590 mole of zinc, times by our stoichiometric ratio between zinc down the bottom to get rid of that unit and HCl up the top to introduce it. What's in front of the HCl? 2. What's in front of the zinc? 1. So we're going to multiply that by 2. And it equals 0.06118 moles of HCl needed. Now it's asking for a volume of HCl. I might start over here. Volume of HCl is going to equal our moles of HCl divided by our moles per litre HCl. So our concentration. So it's going to equal our 0.06118 moles divided by our concentration from our question, 1.47 moles per litre, and that will give us our volume that we need, divided by 1.47 equals 0.041619 litres. Okay, let's look at significant figures. Got 2 in 2.0 and 3 in 1.47, and our molar masses are all 4, so we're limited to 2. So that 4 and that 1. 6 is after that, so it's going to equal 0.042 litres. 2 sig figs, or 42 millilitres. Alright, let's work on this next problem. What mass of insoluble barium sulfate product will form when that volume and that concentration of barium chloride is mixed with that volume and that concentration of potassium sulfate? We've got a precipitation reaction happening here. Okay, let's do an equation. Okay, barium chloride. Okay, it's 2 chlorides for 1 barium. Oh, I'm zooming in. Potassium sulfate. Sulfate is SO4 2 minus, so 2 potassiums. And we're going to form barium sulfate. Just 1 barium to 1 sulfate, 2 plus and 2 minus. That is our solid product. What do we got left over? The potassium chloride and 2 moles of potassium chloride. And that is soluble. Okay, so it's asking for a mass. Question mark. Or not a 2. Erase. That's a better question mark. So it's given us how much? Okay, how much barium chloride solution? So we've got 50.0 mil of 0.20 mole per litre. And the potassium sulfate is 75.0 millilitres, and it's 0.18 mole per litre. Okay, we've got a limiting reagent problem. How much is going to be formed? Well, we need to find out the number of moles of each. So I'm going to draw a line down there. Our moles of barium chloride is going to equal our concentration times our volume in litres. Zero point two times 0.05, 0.01 moles. And for our potassium sulfate, our mole's going to equal 0.18 moles per litre times it by 0.0750 litres. 0.18, 0.075, 0.0135. Okay, now the good thing about this one is it's a 1-to-1 in the reactants and for our products too. So it can directly compare the number of moles and say which one's bigger, which one's smaller. Okay, so we can see that barium chloride is slightly less than potassium sulfate. So barium chloride is limiting, and the potassium sulfate is in excess. A nice easy one. Okay, the limiting reagent is going to dictate how much barium sulfate will form. Okay, because the reaction is going to stop once all the barium chloride has disappeared. Okay, so the moles of the barium sulfate formed is going to equal the 0.0100 moles of the limiting reagent times by the molar ratio between the two. Okay, barium chloride on the bottom and barium sulfate on top. Okay, what's in front of each? A 1 and a 1. So we're going to form 0.0100 moles of barium sulfate. Question, what mass of insoluble barium sulfate? Okay, so the mass of barium sulfate formed is going to equal the number of moles times by the molar mass. So we've got 1 barium, 137.33, plus the 1 sulfur, 32.07, plus the 4 times the oxygen, which is 16, grams per mole. Don't forget those brackets there. So 0.01 times by bracket. Don't forget the order of operations there. 137.33 for the barium, plus the 32.07 for the sulfur, plus the 4 times 16 for the oxygen, end bracket. 2.334 grams. Okay, significant figures. 3 in the 50, 2 in the 0.20 moles per litre, 3 in the 75.0, and 2 in the 0.18. So we need to report that to 2. The 2 and the first 3. The third one is a 3, so it just sticks. So the second one stays the same. So 2.3 grams to 2 sig figs. Squished down there in the right-hand side. All right. I'm going to leave it there. There's some check your understandings to do. Thanks for listening.